Hello there. In this video, our primary topic of discussion would be that of binary operations, which I feel is a good place to start a solid discussion of abstract algebra. We will begin by reviewing some basic notions and fundamentals associated with relations, functions, and then lead into a discussion of what a binary operation is, what it means for an operation to be closed for a particular set, and what it means for that operation to be commutative and/or associative. Throughout our discussion, we will be given a series of 3 examples for you to measure your understanding. Feel free to drop your answers in the comment and discussion section below. Let's get started. Alright, so let's start talking about some of the basics associated to functions and relations, and then we can start talking about binary operations and all the things associated to it. So let's begin by defining a mapping. Let's call that mapping F. And let's assume F is going to map the set D to a set C. So let's draw a little picture to sort of illustrate what we're talking about here. So this is going to be D, and this larger set is going to be C. And let's pick an element in D, and let's call it X. And let's choose an element over here, Y. And let's also put Y in a subset of C, and I'm going to call this set R. And F is going to map X to Y, right? And sometimes we represent this in notation as f of x is equal to y. So this set D is sometimes referred to as the domain of F, and some people abbreviate that as DOM of F. This set R here, so the set R, so R is sometimes referred to as the range, which some people abbreviate as R, or RAN of F. And the set C is called the codomain, CODOM of F. And we clearly see based upon this picture that the range must be a subset or a proper subset of the codomain. So the codomain is the set of all allowed values for the output of the mapping F, and R is the set of all possible outputs that are obtainable from elements from the domain D. Okay, so this is the general notion of functions and relations. Well, this is the general notion of relation. And we say that this mapping F is a function if there exists a unique output for every distinct input value x, right? So for example, x is equal to y squared would not be a function, but it would be a relation, of course, right? So let us look at a particular example that we're going to be looking at in particular. So let's consider the mapping G from the Cartesian product of R with R to the set R, right? Such that G is going to take an element in R, the first R, X, and a second element in the second R, Y. And let's define it to be equal to x squared plus y squared. So this element x squared plus y squared should be an element of a subset of the set of real numbers here, right? Now it could be all of R, but it most of the time is a proper subset. It really depends on this property of G, right? So we clearly see if x and y are both real numbers, we know that x squared that has a particular range from 0 to infinity, inclusive on 0. And the same thing goes for y squared as well. So we clearly should be able to see that the range of this particular function g is going to be the set of all numbers z, such that z is greater than or equal to 0, right? Which is, of course, a proper subset of the set of real numbers, but that would be the particular range, right? So sometimes we do not represent this mapping notation in terms of the range because sometimes it really depends, or sometimes this is extremely difficult to describe the set of range values. Some even polynomials of, say, degree 10, where it has all the coefficients from 9 down to 0, that would in general be a little bit more difficult to determine the upper bound or the lower bound, depending on the leading coefficient of what you're working with here, right? So some people also, this set here, the set of all non-negative reals, sometimes we abbreviate this as R subscript with a greater than or equal to 0. I've seen some people use R with a superscript of plus, but that usually excludes 0. So every time we're going to be working with non-negative reals, we're going to be using this notation, R subscript greater than or equal to 0. Okay, So let's talk about the set of binary operations. Because we see for this particular example, we have two inputs, right? Sometimes people will refer to this as a binary function. So what exactly is a binary operation? So definition. So let S be a non-empty set, right? Because if we have empty sets for the domain or domain sets, part of the Cartesian product, we can't choose elements x and y inside of them, right? So we should mandate that these sets are non-empty. And define star, which is going to map an set S cross S into C. Then star is called a binary operation. Some people will define a binary operation by defining this to be equal to S as well, but we're going to keep it a little bit more open because if I just define it to be S, sometimes when we choose elements in S and S, it might map to something that is outside of S on some occasions. So I'm just going to let this be C, and I'll illustrate why in just a moment. All right, so let's look at a particular example, and let's define an operation. So let's define the set S to be the set of all numbers containing 1 and 2. Now let's define star via a table, because this is usually how we start learning, say, addition, subtraction, all those things in the past. So let this be 1, 2, and let this be 1, 2. So it's going to map S cross S into some elements. And let's define the outputs. So 1 and 1 should be associated to 1. Let's define that to be 2, 2, and let that be 4. Right? So this appears to be ordinary multiplication, right? Or it could be just some random rule that happens to have the same exact outputs as ordinary multiplication. It's really hard to say just giving these four possible outputs. So how would we possibly read this table? So sometimes people will say star 2, 2 is equal to 4. Some people will rewrite this notation instead as 2 star 2 is equal to 4. Those two things are, of course, equivalent notations. And it should also be mentioned, for example, like 5 plus 7 is equal to 12 can also be represented in binary function notation form. In particular, plus 5, 7, because it sends 5, 7 into the element 12, right? So these notations are used interchangeably. It really depends on what we're trying to do and what we're trying to illustrate or conversate to the particular audience. Okay? So that is an example of a binary operation. So let's also consider another example. So example 2. Let's consider the same exact set S. So S is going to be, again, 1, 2. And let's define star from S cross S into some codomain C. We don't exactly know what that codomain C is. So let's just choose that codomain to be R, such that star of x and y is going to be defined to be equal to x plus y all over x plus y plus 1, right? So we're changing these two. So we're doing addition and multiplication and division with real numbers, so I can comfortably choose my codomain to be R, right? And of course, it's going to be a subset of R, a finite subset of R, because I have a finite number of inputs, right? So if I want to generate the multiplication table, if you may, we can definitely do that, right? So star, so 1, 2, 1, 2 are going to be our outputs, right? So what would happen if we put 1 and 1 into this table? So we have 1 plus 1, that's 2. 1 times 1 is 1 plus 1 is 2. So we have 2 divided by 2, that's going to be 1. And then we can do the same for 1 and 2. So 1 plus 2 is going to be 3 on the top, same with 2 plus 1. 2 times 1 and 1 times 2 are both equal to 2, and 2 plus 1 is equal to 3. So we have 3 divided by 3 this, so that's going to be 1 over 1. And then when we plug 2 into both x and y, we have 2 plus 2 is going to be 4. 2 times 2 is 4, plus 1 is going to be 5. So we get 4 fifths as our element for 2, 2. So we can clearly see that the range for this particular mapping star is going to be the set of values 1 4/5, right? Which is clearly a subset of our codomain R. Let us define S to be the set containing the values 1, 2, and a half, and define delta to map S cross S into R by delta xy is equal to x plus y all over x times y plus 1. If you use the input values 1/2 and 1/2 as the values of x and y, what will delta map 1/2 comma 1/2 into? All right, so let's begin talking about another concept associated to binary operations between sets, and that's the idea of closure. So let's begin with the definition of what it means to be closed. So we say a set S is closed under this binary operation star if star x cross y, or star xy, which is of course equivalent to writing x star y, is an element of S for every xy in the set S. So in terms of the range and codomain, that means the range of this mapping star needs to be a subset of this particular set S. It doesn't need to be equal to S, but you cannot have values in the range of star that are not inside of S. So that's the requirement for S to be closed under star. So let's look at a very basic example here. So let's look at the set containing the elements -1, 1, and let's define star from S cross S into S via the following little table. Let's -1, 1, -1, 1. Now let's define it to be, standard multiplication. So that's going to be 1, -1, -1, and 1. So a question that one should be able to answer is S closed under star? So is S closed under star? Well, we can clearly see that all of these elements, 1, -1, -1, all of these are an element of S, right? So therefore the answer would be yes. So if we define it in another way, so that's the case where the range is precisely equal to S, right? But of course it does not need to be equal to, it can be a subset, so -1, 1, -1, 1, we can just define everything to be 1. Again, all of these values are still an element of S, so therefore it's still closed. But we can define the mapping from -1 to 1. And another way, for example, we can make this -1, 1, 1, and 5. We clearly see that this 5 is not an element of S. So therefore, if this is the definition of the binary operation, that means not closed. So actually, we should define this to be another operation, say square. So S not closed under square. And I guess we should redefine that since I don't want any ambiguity here. So we can call that, say, triangle or something like that, right? So there's 3 different binary operations on S, but we clearly see that star, triangle are both closed, but square is not a closed operation for S. Okay, so let's look at another example because we've just been working with sizes of 2 sets, but of course the sets can definitely be a little bit larger. So let's define the set T to be the set containing 1, 0, -1. And let's define what other kind of shapes do we have here. Let's do upside down triangle. So -1, 0, 1, -1, 0, 1. And how do we want to define this? Let's define upside down triangle, or nabla as some people call it, to be like addition, standard addition. So that's going to be -2, -1, 0. That's going to be equal to -1, 0, 1. This is going to be 0, 1, and 2. So if we define nabla this way, is T closed under nabla, right? So question, is T closed under this operation, upside down triangle, right? So you need to be able to look at this table, and if you're not given a table, you should be able to generate one or be able to pick numbers on the output, sort of like we did for that triangle relation a little bit earlier, and see if there's any elements in this little box that are not in the original set. So we clearly see we have -2 and 2, and these two numbers here, right? These are not an element of. We're working with T, not S here, right? So these elements are not in T. There are other values here, right? So we could easily redefine this operation. For example, we can redefine -2 and 2 to both be equal to 0. Then we'll have a nice little symmetric kind of table here. But that's not the problem that's given here, right? So in this particular case, we clearly see that T is not closed under this operation, upside down triangle. And that's the idea of closure for a particular set under an operation. So let us define O to be the set containing the values of all x such that x can be represented in the form 2k plus 1, where k is an element of the set of integers, in general, the odd integers. If star is defined as ordinary multiplication and star maps O cross O into R, is O closed under star? Justify your answer. Alright, so the last thing I want to talk about in this introduction to binary operations on sets is the idea of commutativity and associativity for operations. And these concepts you've probably already been introduced to, so I just want to make sure that those things are solid. So let us consider the set S, and let us consider S to be the set containing the values alpha and beta, and let's define a new operation star to be the set containing the values alpha, beta, and let's define the output values of star under the set S to be equal to, say, alpha, beta, and alpha, beta. So the definition for commutativity is the following. So star is said to be commutative if x star y is equal to y star x for all pairs xy in the set containing these values. And the idea for associativity you should also be familiar with. So we say star is associative if x star y star z is equal to x star y star z for all triples x, y, z, and s. So with these two definitions of commutativity and associativity, we can then ask the question, is this set S containing alpha beta with this particular multiplication table commutative and or associative? So commutativity is usually easy to show. So we can look at, for example, alpha star alpha. Alpha star alpha is equal to alpha. And if we just reverse these values of alpha, we still get alpha. So that's sort of vacuously true. And the same thing is going to go for beta star beta, which is going to be beta, because if we reverse these two values, we still get beta. So that's not too exciting. So what's exciting or not so trivial is when you have two different values here. So let's look at alpha star beta. So alpha star beta in this case would be equal to beta, and beta star alpha in this case is going to be equal to alpha. So for this operation star to be commutative, these two must be equal for all pairings first element star second element. And we clearly see for this particular example that these are not equal. Therefore, star is not a commutative operator for this particular set S. Okay, or star is not commutative. Okay. Now the idea of associativity, sometimes this can be a little annoying to solve, and you should see why in just a moment. So let's look at a few examples. So let's look at alpha star beta star alpha, right? So alpha star beta, if we look at the table that we had before, so let's just scroll up a little bit. So alpha star beta in this case is going to be equal to beta, and then beta star alpha is going to be alpha, right? So alpha star beta is going to be equal to beta, and beta star alpha is going to be equal to alpha. And then we need to change the position of these parentheses. So we need to consider alpha star, beta star alpha, and beta star alpha, that's going to be equal to alpha, and alpha star alpha is equal to alpha. So these check out. So that's a good thing, but we need to check all possible triple combinations for these two elements, right? So let's consider another one. So let's consider beta star beta star alpha. So beta star beta, in case you don't remember, was equal to beta, and beta star alpha is equal to alpha. And if we change the orders of these parentheses, so beta star alpha, so beta star alpha was equal to alpha, and beta star alpha is equal to alpha, and we clearly see that these two are also equal. So you need to continue this for all possible triples. So all possible triples, x, y, z, for this particular associativity test, right? But if you look at all the possible combinations, you should be able to see that yes, it is. And what do I mean by yes, it is? What I'm saying here is that star is associative on this particular set. S, that's a weird looking S, right? So there we go. So how many different triples do we need to check for this particular type of associativity test, right? So let us suppose that the set S is equal to n. So there's n distinct elements, and let's assume that this number n is finite. So by the fundamental counting principle, which you probably encountered in statistics or probability theory or something like that, we're going to have n times n times n different types of triples, because technically it's possible that alpha star alpha star alpha, and when I say that, so what I mean by, so alpha star alpha, it's possible that this is not the same as alpha star alpha, if I define this binary operation star in some particular way. So we need to check both values for the same and also the different values. And we're assuming that there's n different values in this particular set. So we clearly see that there's going to be n cubed different statements that we need to check here. So therefore, for our particular example, where S is equal to the set containing alpha and beta, we clearly see that the size of S is equal to 2. That means we need to check n cubed, which is equal to 2 cubed, which is equal to 8, different operations to check, right? We only check 2, but there's 6 more that we need to check for associativity. So we can clearly see if the set is extremely large. Checking for associativity can sometimes be tedious, but not necessarily difficult. So if n is large, it might take a while. There are algorithms that can reduce the size from n cubed down to something a little bit smaller, but we're not going to talk about that here because generally, as long as you have one method, you can technically do all of them, right? So those are just the basic ideas associated to the commutativity and the associativity of binary operations, and we're definitely going to be talking about these two properties in the upcoming videos in more detail. Let us define delta again to map r cross r into r via the relation delta xy is equal to x plus y all over x times y plus 1. Is delta commutative and or associative on the set R? Justify your answer. As always, if you enjoyed, please like this video, consider leaving a comment, and if you enjoy the channel content, please subscribe. We publish several new topics every single week. Thank you.